Deep dive into sklearn's LarsCV. LarsCV stands for Least Angle Regression with Cross-Validation. It's a powerful tool within scikit-learn for finding the optimal complexity of a linear model. Balancing bias and variance through the clever use of cross-validation. Let's break down its components. 1. Least Angle Regression Lars. Foundation Lars is an algorithm for finding the solution to a linear regression problem. Particularly useful when the number of features is large or there are high correlations between features. Progressive feature selection Lars works iteratively, adding one feature at a time to the model. It chooses the feature that has the highest correlation with the target variable and adds it to the model, gradually building a solution path. Efficient computation Lars is computationally efficient, especially when compared to standard methods like ordinary least squares (OLS) or gradient descent, particularly in high-dimensional datasets. 2. Cross-validation CV. Purpose cross-validation is a technique used to estimate the performance of a model on unseen data. By partitioning the dataset into multiple folds. Model selection in LarsCV. Cross-validation plays a crucial role in selecting the optimal model complexity. It trains the model on different folds of the data, evaluates its performance on the remaining fold, and averages the results to get an unbiased estimate of the generalization error. Finding the best model LarsCV considers a range of model complexities, measured by the number of features included in the model. For each complexity, it performs cross-validation and calculates the estimated generalization error. The model with the lowest error is deemed the best. 3. Key values in the YAML description. Parameters. Fit intercept. This boolean determines whether the model should include an intercept term, a constant term. If true, the model will have a y-intercept, which can improve the model's ability to capture the overall trend in the data. Normalize. This parameter controls whether the features should be normalized before training a model. Normalization is the process of scaling the features to have zero mean and unit standard deviation. This can be beneficial when the features have significantly different scales, which can cause problems for the Lars algorithm. Maxiter. This integer sets the maximum number of iterations that the Lars algorithm can take. This parameter helps prevent the algorithm from running indefinitely, especially in cases where the model might not converge. APES. This float value defines a tolerance for the Kolsky factorization, which is a numerical method used within the Lars algorithm. A smaller APES value generally leads to more accurate results but can increase computation time. CV. This parameter determines how cross-validation should be performed. You can provide an integer to specify the number of folds, or you can pass a custom cross-validation generator, giving you greater control over the splitting process. Njobs. This integer allows you to control the number of CPU cores used to run the cross-validation process in parallel. Setting njobs to -1 will use all available cores, potentially speeding up the process. Verbose. This integer controls the level of verbosity during model training. A higher value will print more information, such as the progress of the algorithm and the scores for each fold. Random state. This parameter is used to control the random number generator used for the cross-validation splitting strategy. Setting a specific value ensures reproducibility of the results. Methods. Fit(x, y). This method trains the model using the input features x and target variables y. The cross-validation process is performed during this step to find the best model complexity. Predict(x). This method uses the trained model to predict the target variable for new input features x. Score x, y. This method computes the R-squared score. a common metric for evaluating the performance of linear regression models. It measures the proportion of the variance in the target variable that is explained by the model. Get_params. This method returns a dictionary containing the current values of all the model parameters. Set_params. Quarks. This method allows you to update the model parameters with new values. Attributes. Core. This array stores the estimated coefficients for each feature in the best model. Intercept. This float value represents the intercept term or constant term in the best model. Niter. This integer stores the number of iterations that the Lars algorithm ran before reaching the best model complexity. Active. This array holds the indices of the features that were selected in the best model. MSE path. This array contains the mean squared error MSE values calculated for each model complexity. During the cross-validation process. CV results. This dictionary stores the detailed results of the cross-validation process, including the mean and standard deviation of the scores for each model complexity, as well as the parameter settings for each model. Best score. This float value represents the best cross-validated score achieved by the model. Best estimator. This attribute holds the actual estimator, the Lars model that achieved the best cross-validated score. Best params. This dictionary stores the specific parameter settings that led to the best performing model. Best index. This integer represents the index of the best performing model within the CV results params array. Refit time. This float value stores the time in seconds taken to train the best model using all the data. Score time. This float value represents the time in seconds taken to calculate the score of the best model on the training data. In essence, LarsCV provides a principled way to find the optimal complexity for a linear regression model. It combines the efficiency of the Lars algorithm with the robustness of cross-validation. By exploring various model sizes and evaluating their generalization error, LarsCV helps you identify the sweet spot where your model strikes a balance between accurately fitting the training data and being able to generalize well to new data.